It's now time to move on to section 5.5, which is substitution. This is a really helpful tool we are going to use a lot throughout every math class. We're going to use it, of course, here in Calculus 1, but then again a lot in Calculus 2 and 3 and on. Sorry, I can't spell and talk at the same time. Substitution. That looks like too many T's, but I think that's right. Sorry about that. Substitution. So I feel like the best way to show you when I need this and what I'm going to do is by doing an example. So let's look at an example. Actually, first things first, let's do a review. So let's do an example review. So let's do the integral of x to the 5th dx. So as we learned in chapter 4, section 10, we learned that pretty much what this wants is it wants the antiderivative of x to the 5th, right? Well, how we said we do that is we add 1 to the power, making it x to the 6th, and then divide it by that new power. So dividing by 6 is like saying times 1/6. But then we said too, we need to add a constant, so I put plus c. So the reverse power rule is that I'm going to add 1 to the power and then divide by that new power, right? Keep that in mind. We are going to use that. Okay, now let's look at an example where I might need substitution. Let's do the integral of 6x times the quantity 3x squared plus 4 raised to the 4th dx. Now looking at this straight up, it looks pretty hard. It looks like we can't do this one because there's a lot of terms, there's a lot of moving parts, and so it's not as clear as, like, say, this one we just did here. But remember the point of what I'm trying to do, right? Basically, this is a derivative, and so I want to know what function has the derivative I see here. So let's think this through. Remember, let's try to think back to a time where I took a derivative and then had to multiply it by something else, right? Well, that sounds a lot like the chain rule, right? Because whenever we do the chain rule, I take the big derivative first, and then I multiply that by the derivative of the inside stuff. That looks kind of like what I did here, because I have a big term times something a lot smaller. So what this means is it looks like they did the chain rule here. And so I want to try to go backwards, okay? So what I want to do in order to go backwards is I want to see what could that inside stuff have been, okay? Well, if I look right here, inside of this is 3x squared plus 4. Well, if this was the inside stuff, I would have had to multiply by the derivative of that. Well, the derivative of 3x squared plus 4, bring down my a2, and I get 6x. Well, look what I have right here is 6x. So what this means is we did the chain rule with the inside stuff being 3x squared plus 4. So now that I see that the inside stuff is 3x squared plus 4, I'm going to let that be a u. I'm going to let that be u. So 3x squared plus 4 is going to be my u. So, but notice here this is dx, which means I need it in terms of an x. So if I'm changing it to a u, I need this to be du. So what I do is I find the derivative of the u. Well, like I said, bring my 2 down. That's going to be 6x dx. So I can rewrite this in terms of the u because 6x dx transforms into du, and then 3x squared plus 4 to the 4th becomes u to the 4th. So what this actually is u to the 4th du. Again, I got that because 3x squared plus 4 is the u, so that's u to the fourth. And then as I saw right here, du is equal to 6x dx, which I have right here, so that becomes du. Now, this looks exactly like how that one did here. Just add 1 to the power. That's going to be u to the fifth. Then divide it by that new power. So that's going to be 1/5 u to the fifth plus c. But I started with dx, and so I need to end it with an x. So I know u is equal to 3x squared plus 4. So just plug that back in for the u. So 1/5 times 3x squared plus 4 to the fifth plus c. So the key here is if I see one that looks a little hard, it looks like there's a lot of terms, it looks like a whole mess. What I want to do is I want to see, is there a u in here where the derivative is there too? So I'm raising a bunch of stuff to the fourth, so why don't I try and let u be that stuff? So u equals 3x squared plus 4. The derivative of that would be 6x, which I have. So I'm going to let u be 3x squared plus 4. So du is equal to 6x dx, which means I can rewrite this as u to the fourth times du. Let's do another example. Let's do the integral of 3x squared times x cubed minus 3 squared dx. So the same thing here. This is a lot of terms that looks like a whole mess. I want to try to rewrite this into a term that's not very hard. So here I can see I have some stuff squared. So let's see what happens if I let u be equal to that stuff. Well, then the derivative of that, bring the 3 down, makes it 3x squared dx. Well, if I look, I have 3x squared dx there, so then that will help me. So, like I said, I let u be equal to x cubed minus 3, so this becomes u squared, and then 3x squared dx is now du. So now here I'll just add 1, which would make it u to the third, divide by 3, so 1/3 u to the third plus c, and then plug in what we said the u was. So that's going to be 1/3 times x cubed minus 3 cubed plus c. Just like that. Another example. Integral of z times the square root of z squared minus 5 dz. Now here, this looks really hard, right? Because I have z times a square root with some z's in it. There's just a lot of terms here, so just like we said right up here, it would be helpful if I can rewrite this so that it's not that bad, right? So since I have the square root of some stuff, it would be nice if my u could be that stuff. So let's let u be equal to z squared minus 5 and see what I can do there. Well, I would need a du, so then I'm going to take the derivative. The derivative of z squared minus 5, bring down my 2, gives me 2z dz. Now, what I have is a z, but I need 2z. So this isn't quite right quite yet, but I can make it work out. So I need 2z. So what happens if I put a 2 right here? Let me move my sigma sign. Let's put a 2 right here. 2z. That's great. That's fine. However, it is not mathematically correct to just put a 2 there, right? That doesn't make sense. I can't just put 2 there. If I'm going to put a 2 there, I need to also put a 1/2. Because 1/2 times 2 is equal to 1. And so then that's fine. I can do that. Again, I needed 2z. All I had was a z. So I can put a 2 there. But if I put a 2 there, I have to also put a 1/2 to balance it out. Okay. So what I end up with, this 1/2 out front will stay. 1/2 integral of 2z dz becomes my du. And this becomes the square root of, I said that was equal to u. Square root of u is like saying u to the 1/2. So one more time, I wrote the square root as a 1/2, and this is my u, so u to the 1/2, and then 2z dz became du. So again, I just need to add 1 to the power here. 1/2 plus a 1 is 3/2, and then I need to divide by the new power. 1/2 divided by 3/2 is like doing 1/2 times 2/3. So the 2's cancel out, and we have power of a 1/3. So this is 1/3 u to the 3/2 plus c. Remember to put the plus c there, that's a big deal. And then we said u was equal to z squared minus 5, so that makes it 1/3 times z squared minus 5 to the 3/2 plus c. So again, if it isn't exactly right, just like how here I needed a 2z, but I only had a 1z, I can put a 2 there. Just make sure you also put a 1/2. Another example. Integral of x squared times x cubed plus 5 to the 9th dx. Once again here, if I look at this isn't in a form yet I can quite do, and so then I want to change this whatever way that I can. I have stuff raised to the 9th, so I'm going to let u be equal to that stuff, so x cubed plus 5. And so du, the derivative, bring my 3 down, would make it 3x squared dx. So a lot like on the last one, I need 3x squared, but I only have 1x squared. So that's okay as long as I put a 1/3 out front to balance it out. So this would become 1/3 integral of, we let u be equal to x cubed plus 5, so that's u to the 9th. And then 3x squared dx becomes du. Again, I put this 1/3 here because I need a 3, but I don't have one. So in order to put a 3 there, I have to also put a 1/3 there. Again, add 1. So 1/3 u to the 10th, and then divide it by the new power. 1/3 times 1/10 is 1/30th. And we said u was equal to x cubed plus 5. Just like that. Another example, this one's really neat. I like this one a lot. This one is the integral of sine of t over cosine cubed of t dt. Now this one for sure, I look at this and it's like, what the heck is this, right? So again, we need to try to rewrite this as much as I can. So just like on the last one, how I had stuff raised to the 9th, and so then I let that be my u, I'm going to do the same thing here. Here I have cosine raised to the 3rd. So since cosine is being raised to the 3rd, let's try letting that be equal to the u. So let's let u be equal to cosine of t. The derivative of that, the derivative of cosine is negative sine. So I have sine of t, so to make it negative sine of t, I need to put a minus sign out front too. So to make this negative sine of t, I need a negative out front too. So this becomes negative integral. Negative sine of t dt just becomes du. Easy enough. This becomes 1 over u cubed, which I could write as u to the negative 3rd. Again, it's in the denominator, and so it would be negative 3. Add 1 to that. That would be u to the power of negative 2 over my new power, which is negative 2 plus c. Negative 1 divided by negative 2 gives you positive 1/2. My u is equal to cosine. So it's cosine squared, but since it's a negative, it's going to be in the denominator. Plus c. Again, because this is cosine to the power of negative 2, which means I can put it in the denominator as being squared. Another example. Let's do the integral of cosine of t over sine of t dt. So this one isn't as clear as the last one was because I don't have one of these to a power, right? So for this one, I might just have to think it through. If I let u be equal to cosine, then du would be equal to negative sine t dt, right? But notice here, sine t is in the denominator, which means I'm doing dt divided by sine of t. If I let u be equal to cosine, du would be negative sine times dt. So that wouldn't work then because I am dividing it. So that doesn't quite work out. So instead, let's see what happens if I let u be equal to sine of t. In this case, du, the derivative of sine is cosine. And look at that. Cosine t dt, I have that. So this would become just the integral of 1 over, that's my u, cosine t dt is du. So now I've got to think about what the antiderivative of 1 over u is. Well, that is the natural log of the absolute value of u. And u is equal to sine of t. So that's the natural log of the absolute value of sine of t plus c. All right, so now I can also apply these to definite integrals. So here's an example. Let's do the integral from 0 to 1 of x squared times 1 plus 2x cubed to the 5th dx. So we learned in sections 5.2 and 5.3 that how I'm going to do this is I'm going to find the antiderivative and then plug in a 1, plug in 0, and then subtract them. Okay. So first things first is I have to find the antiderivative. So just like we have seen, I have a bunch of stuff to the 5th, and so let's try and let this be equal to the u. So 1 plus 2x to the 3rd, let's see what happens there. Du, the derivative of 1 plus 2x to the 3rd, bring the 3 down, and we get 6x squared dx. Now what I have is x squared, but I need 6x squared, so I want a 6 right there, but I can't just put it there. I have to multiply by 1/6. Integral of, we let this be the u, so u to the 5th, and 6x squared times dx is du. Now, for the bounds, you have two choices on what you could do here. The first choice is to just not put the bounds until the very end. And that'll work. Okay, so like I could solve this just like I did right here, and then plug in the bounds whenever I get done. Or I can go ahead and change my bounds. This was dx, which means these are in terms of the x. So now that I'm in du, I can change them to in terms of the u instead. So let's do that. So how about I change these into a u? So when x is equal to 0, u is equal to 1 plus 2 times 0 cubed. That just becomes a 1. So my lower bound is now a 1. Again, because I plugged 0 into here to figure out what the u is. Do the same thing for 1. U equals 1 plus 2 times 1 cubed. 1 cubed is 1. 1 times 2 is 2. 1 plus 2 is 3. So the top bound is now 3. Now, since I changed my bounds to be in terms of a u now, I don't have to do this last step right here where I plug back in what the u is, because I have changed everything to u's. So now I can just take the antiderivative, 1/6 times, add 1, and we get u to the 6th over 6. And we're doing that from 1 to 3. Plug in a 3. 3 to the 6th is something that I don't know. I'm getting my calculator. 3 to the 6th is 729 divided by 6 times 6, which is 36. And you get a fraction of 81 over 4. Again, that's what happens if I plug in a 3. Now if I plug in a 1, subtract that, plug in a 1, 1 to the 6 is equal to 1, so that's 1 over 36. We need a common denominator, which would be 36, so let's multiply that by 9. 729 over 36 minus 1 over 36 gives you 728 over 36, which reduces down to 182 over 9. So again, since we changed our bounds into the u, I don't have to go back in and plug in what the u was like I did here. Right here, after I got that, I plugged in the u. I don't have to now because I changed my bounds to be in terms of the u. So this is done the same way, except make sure I change my bounds. Let's do some more examples. Integral from -1 to 0 of y times the quantity 2y squared minus 3 to the 5th dy. So just like the last ones I have done, I see here I have a whole lot of terms, so I don't really like this, so I want to try to rewrite this, okay? So I have some stuff to the 5th, so I want to let u be that stuff. And see if that helps us. If it does help us, I should be able to take the derivative. The derivative of 2y squared minus 3 is going to be 4y dy. I have y, I need 4y, which means I need to multiply it by 1/4. Again, because I want 4y, but I can't just put a 4 there, right? So I need to multiply it by 1/4. Integral of, we are going to worry about our bounds here in a second. This is 2y squared minus 3 to the 5th, but since I let u be equal to 2y squared minus 3, that's just u to the 5th, and 4y dy is now du. Now for the bounds, my bounds now are in terms of a y. I need them in terms of the u. So for x equals -1, u equals 2 times -1 squared minus 3. The -1 squared is 1. 2 times 1 is 2. 2 minus 3 is -1. So that bound stays the same. That's helpful. For x equals 0, u equals 2 times 0 squared minus 3. 0 squared is 0. 0 minus 3 is -3. So now I just need to take the antiderivative of u to the 5th. That would be u to the 6th over 6. Since it's over 6 and I currently have a 4, I can write that as 1 over 24 u to the 6th. Again, because I would add a 1, which would make it 6. Divide by 6, I'm already dividing by the 4, So it's 1 over 24 u to the 6th. And I'm doing that from -1 to -3. -3 to the 6th is equal to 729. 729 over 24 reduces down to 243 over 8. Minus, plug in -1. -1 to the 6th is just equal to 1, so 1 over 24. I need a common denominator, which would be 3, so 729 over 24 minus 1 over 24 gives us 728 over 24. Reduce that, and we get 91 over 3. So that's why it is really good to change the bounds, because then I don't have to go back and substitute in what the u was. Another example. Integral of x times e to the 4x squared plus 3 dx. So this one definitely looks hard because I have an e in there, I have an x, the power is all weird and everything. Let's see if I can try to rewrite this into a form that's not that hard, okay? So here I can see I have e raised to some stuff, right? Well, as we have said in Calculus 1, we like e because e always just stays e, right? The derivative of e is just e, so I like e. Here I have e raised to some stuff. So let's let that stuff be the u. The derivative of that stuff then, 4x squared, bring down our 2, that makes it 8x dx. I have an x, but I need 8x, so let's multiply that by 1/8. Integral of 4x squared plus 3 is now my u, and then x dx is now inside of my du. Oh, I forgot the bounds. This should be from 0 to 1. So sorry about that. 0 to 1 of all this. So now I need to change my bounds to be in terms of the u. So when x is equal to 0, u is equal to 4 times 0 squared plus 3, which is 3. And then when x is equal to 1, u is equal to 4 times 1 squared plus 3. 1 squared is 1. 1 times 4 is 4. 4 plus 3 is 7. So now I just have to take the antiderivative of e to the u, but as we've said, we really like e because e just stays e, right? So e to the u just remains e to the u. And we're doing that from 3 to 7. Plug 7 in first, that's 1/8 e to the 7, minus, then plug in a 3. And we can just leave it like that. That's perfectly fine right there. I have one more example that I want to do. Then we will call it good. This is going to be the integral from 0 to 1 of x squared cosine of pi over 2 x cubed dx. Now this one definitely for sure looks really gross, right? And so like we said, we want to try to rewrite this into a form that's not that hard, okay? So I have cosine of some stuff, so let's let u be that stuff. Pi over 2 x to the 3rd. So let's take the derivative of that. Bring down my 3 would make it 3 pi over 2 x, that's now squared. Again, we just brought our 3 down, making it 3 pi over 2 x squared. I have an x squared, but I need 3 pi over 2. So in order to put 3 pi over 2 right here, we need to multiply it by 2 over 3 pi. Again, because I want 3 pi over 2 here, I don't have it. So in order to put it there, I need to multiply out front by 2 over 3 pi. integral of cosine, that's now u, so cosine of u, x squared dx goes into the du. Now I need to change my bounds. So when x is equal to 0, u is equal to pi over 2 times 0 cubed. Well, that is not too bad. That's just 0. When x is equal to 1, u is equal to pi over 2 times 1 cubed. 1 cubed is equal to 1. 1 times pi over 2 is pi over 2. So now I need to take the antiderivative of cosine. Well, that would be sine, because the derivative of sine is equal to cosine. So that's 2 over 3 pi times sine of u. Doing that from 0 to pi over 2. Plug in pi over 2. 2 over 3 pi times sine of pi over 2. Minus, plug in a 0. Sine of pi over 2, if we get our unit circle out. I always lose my unit circle when I need it. There it is. Sine of pi over 2. Pi over 2 is right here. Sine is equal to 1. So sine of pi over 2 is 1. Giving me 2 over 3 pi. Minus sine of 0. 0 is right here. Sine of 0 is 0. So I just get 2 over 3 pi.